to get a random sample of 5 out of our sample of 22 from last year's scores. You guys remember, you go to math, and then you slide over to probability, and you're looking for, you guys remember? Random integers. Beautiful. We're looking for random integers. Remember, you need your lower boundary, your upper boundary. So the first student was labeled as number 1. Your last one was 22. And then your sample size that you're choosing samples of 5. You're going to list those scores and then find the averages of them. And then you're going to repeat that 4 times. Make sure that when you write these functions down that you are not picking repeating numbers. So if you get the same student twice, you need to generate a new sample, right? Does that make sense? Hopefully it does. So yeah, find your 4 thingies, and then what we're going to do, it says we're going to write each mean on a different sticker and put a dot on the appropriate location. We're not going to do that. We're just going to make a dot plot on the whiteboard, and then I'm just going to use some wipey things to wipe it down. So we will draw our distribution on paper once we've done it on our whiteboard in just a second. So yeah, find your averages. So once you have this dot plot on your paper of all of these average scores of size 5, once again, this isn't a perfect sampling distribution. This is just an approximation. Of a sampling distribution. And remember, the reason for that is we probably don't have every dot of every possible sample of size 5 from this group of 22. I think there would have to be thousands of dots on the board for us to do that, and we can't guarantee that we have all of them, but we have a pretty darn good picture of what it's going to look like, right? So what does 1 dot on each poster, or what does 1 dot on the whiteboard represent? Once again, that's 1 average exam score from a sample of 5. And then where would we approximate, where do we think the actual average is? If we were to put that on a graph, I'd say somewhere between 80 and 90, right? Maybe closer to 80 to 85. I don't know. What do you think? Why don't you guys all make a guess, and whoever gets closest will get a Jolly Rancher. Eh? Make your guess. Where is your mean going to go based on your graph? Let's see how good of an approximation you guys can get. Use decimals. Percent. Personally, I would have put it, I don't know, around 84-ish, maybe. The reason for that is it looks like we do have some lower scores that we're dragging that down a little bit. If you had somewhere around 85, last year they put it around 85. I'm frozen. Sorry, guys. Thanks. Last year, my students put this around 85-ish or 86, just because so much of the data was between 80 and 90. So any estimate between like 80 and 87 would have been good. But once again, here's our actual average. A sampling distribution, though, shows all of the possible combinations of dots. Remember, this is the NCR thing that we talked about way back in Chapter 5. This is the combinations. Do you guys remember where to find that in your calculator? It's actually just where you were for random integer, right? If you keep scrolling, you should go to math and then to probability. Right? So we're looking at the number of combinations. So we need the total number of dots. needed for to be a sampling distribution, right? So if we are looking at NCR, this is a little confusing. What should N be? In this case, your N's not 5, your N is the 22, and you're choosing the R, so you're choosing the 5. So you should have this function, oops, I should put a 5 here. You should have this function to talk about the number of combinations that you would need to have a true sampling distribution. Somebody give me that number. Should be big. 26,334? Wow. We definitely don't have all the dots, right? We're not even close. We do have a good sampling distribution, but definitely don't have enough, right? There's definitely not enough on our graph. We probably have about 100 on our graph, which is good, but not good enough. So we took a random sample of 5 midterm scores at Fowler and got a mean of a 68. Is this a convincing evidence that Fowler students did worse than our school? So if we were to do this like full-on AP exam, we're looking at convincing evidence, right? We're looking at what are the chances that we got an average of 68 or less by chance, right? So we need to figure this out based on our dot plot, right? How likely is it, if Fowler had the same scores that we did, how likely is it that we got a 68 as an average by random chance? So in this case, I think I see maybe 1 dot, right? We're going to pretend it's at or below 68. I think it was like 69, but we'll pretend it's a 68. Out of, in this case, there's 26 of you. 26 times 4 is 104. So that percentage is what, less than 1%? Somebody put that in their calculator for me. It's going to be 0.00 something, right? Is this convincing evidence then? Is it good or bad that we have a really small chance? Is it going to help our cause? It actually is, right? So the fact that we got an average of a 68 should hint, ooh, that probably shouldn't have happened by random chance unless something real funky was going on, right? So since our probability was so low, whoops, here's what I would write. Since our probability remember was so low, usually, do you remember the number we compared it to? 5%, right? So since our probability was less than 5%, we have convincing evidence that we didn't get an average of a 68 by random chance, right? Sorry, I'm running out of space there. So once again, since our probability was so low, we have convincing evidence that we didn't get an average of a 68 by random chance. More than likely, Fowler did worse on this exam than we did. Does that make sense? Okay, let's get to the big ideas. So, important ideas are going to relate to that sampling distribution we talked about. Big thing we need to talk about is the variability involved of a sampling distribution or an approximation of a sampling distribution. If we increase sample size, if we increase the sample size of a sampling distribution, what should happen to our variability, so the spread of our data? What do you think? Is a bigger sample size going to be a good thing or a bad thing? It's a good thing, right? So if we want it to do good things, would we want higher or lower variability? Probably lower, right? So if we have increasing sample size of a sampling distribution, sorry, this is shifting because my cord here, that should decrease the variability. Sorry, I didn't need this comma here. So it decreases the variability of the distribution. And then obviously vice versa, right? If you were to have smaller sample sizes, then you could easily have more variability, right? So when Kennedy was talking about her sample of 5 and she got like, what, 4 really big or low numbers? If you were picking 2, you could have possibly gotten the 2 lowest scores and been way towards the bottom of the chart, right? But that's pretty impossible when you're picking 5. So anyway, that's the idea of variability. If we're talking about estimators, an unbiased estimator, and this is a good thing, right? Bias is bad, so to be unbiased would be good. So what we want is an unbiased estimator. And what that means is it means we have a statistic is unbiased. Biased. Sorry, I spelled biased without the I. A statistic is unbiased if the mean, if the population, so I'm sorry, if the mean of the sampling distribution is equal to the parameter. So if we were looking at a dot plot, right? I'm just going to sketch one. If we had some dot plot, we would want the center of our distribution to be exactly where our parameter is, right? But if we have something kind of like what we had, where we had an outlier or two off to the left, whoops, sorry, and then we had some data over here, sometimes the mean of our sampling distribution does not match the population mean, right? So this one is bad, right? Because they don't match. There might be a skew. That's unfortunate. Right? So this graph over here is bad because the mean of our distribution, the center of that distribution, might not necessarily match the mean of the population, right? So usually that happens when you have skew in your population somehow. So if we were to actually graph the population of 22 points, if we saw a skew in the population, more than likely we're going to have a biased estimator. But if it's roughly symmetrical, we can get a pretty good unbiased estimator, right? So this check your understanding is a little tricky. I just wanted to kind of set you off in the right direction here. So the histogram on the left shows eruptions in minutes of the Old Faithful geyser for all 222 recorded eruptions during a particular month. For this population, the median is 75 minutes. So I would personally mark that on my paper. The population median is 75. And then it says the sampling distribution over here